Thank you very much, everyone, for being here. And thank you very much to our speaker, Professor Tobias Fischer, who visited us a couple of months ago. And this visit was really great for all of us in geophysics. So today he accepted to give us a seminar on fluids and rifts, and taking as example the East African rift where we are. Tobias, the floor is yours, and thank you very much.
Great. Thank you, Catherine. And also thank you for your kind hosting me at the Institute in March and April earlier this year. It was truly a nice experience and met a lot of great people and had some good discussions. So today I will talk about rifts and fluids and talk about the case of East Africa. A lot of this work isn't super new. I've presented things in various places, but I am trying to put things together and really hope to have some stimulating discussions, maybe afterwards, or some ideas that come up. And so we will make this kind of an interactive talk, hopefully at the end of it. But first of all, I want to jump in and highlight this study. And I see Sasha is online here. And this study has examined the importance of rifting in the past to modulate significantly the atmospheric CO2 content. And what they have showed is that the Mesozoic rift period and Cenozoic rift periods that occurred all of the globe, around the globe, produced high CO2 levels in the atmosphere. And so these models are, of course, very complex and rooted in geodynamics. At the same time, they rely on estimates of CO2 emissions from rifts. And those emissions still remain poorly constrained, as we'll see throughout this talk. The global carbon fluxes, if we just look at some recent work, this was Kellerman and Manning, and then some updated numbers here. And this is now in megatons of carbon per year. For arc volcanoes, we have, the newest number is maybe about 20 megatons of carbon per year. And then we have mid-ocean ridges, 14 to 30 megatons per year. This is Levoyer flux. And then continental rifts is the topic of this talk. And we see that there are very few studies still. There's the study by Hyung-Woo Lee, which my former PhD student, 10 to 28 megatons. And then the study by Hunt et al., which followed just a year after, which is lower in flux significantly, although the 9 is very close to the 10. So, but those, as far as I know, are the only studies currently. So there's still a lot of work to do. Now, if you look globally, again, this is another way of looking at it. And that now looks at or presents the data in teragrams of CO2 per year. So we toggle back and forth between grams of carbon or teragrams of CO2, right? And it's simply conversion. But I'm going to go back and forth between those two things. And what I want to highlight here is that this is volcanic degassing, which is now the arcs and the mantle degassing. And it includes plume degassing, which is about 51 teragrams of CO2 per year. And then the diffuse emissions here, which are quite poorly constrained still, I would say, from 48 to 172 with an average of 92. So the diffused emissions over all this volcanic region, over all these volcanic regions, could potentially be larger than what comes out of volcanic plumes. By volcanic plumes, I mean volcanic craters, hydrothermal emissions close to the volcanic edifice. Diffuse is everything away from the volcano, just coming out of the soil through faults and so on. And then you have tectonic degassing. And tectonic degassing, that's, the continental rifts, for example, are the main contributors here. And then you have the East Africa rift, and then you have the mid-ocean ridges are just shown here for comparison. Okay, so these fluxes, are pretty important to constrain, I think, and a lot of groups have been working on these fluxes to get them to agree and make sense, right? There's still a lot of unknowns. What I'm also showing here is the subduction flux. So that's the other part of the story, how much carbon actually goes into the mantle through subduction. And if we look just at volcanoes, I'm muted. Okay, I guess you missed most of my talk so far. But anyway, I continue here. And for volcanic degassing, we see that most of the emissions from volcanoes during passive degassing come just from about 10 volcanoes globally. This is average from 2005 to 2015. So, about 20 teragrams of CO2 emitted from volcanoes globally comes from 10 volcanoes. And then the next 20 teragrams comes from the next 90. So the 100 volcanoes globally emit, most of the CO2, like 40 teragrams out of the whatever 60 or so teragrams of CO2 it is, right? And then you have all these little guys, gazillions of those little guys that contribute CO2, but not very much overall, right? So that gives you kind of a sense. So now I'm going to give you some applications of how we can use volcanic degassing to get at the carbon contents in the source, right? And I'm going to use Nyiramuagira, Nyiragongo here as an example, because there's some pretty good data, and it's a big emitter of CO2, right? So passive degassing is about, can you see my pointer? Is there a way I can make a pointer? I don't know how to do that. So anyway, you see passive degassing is 1,400 kilotons of CO2 per year, eruptive, 700. And then this is SO2, by the way, then you take the carbon sulfur ratio and you get an eruptive CO2 emission of 2,500. And then total, the total is about 4 megatons of CO2 over 30 years that we have data from, right? So it's a really, really big emitter. Comparatively, Kilauea, 1.1, Etna, 3.3, and Morb is about 56 to 65 megatons of CO2. So it's like 10% of Morb. It's a significant contributor, right? And so where does the CO2 come from? Well, obviously it comes from the magma. And if you have a magma flux estimate, you can then very easily compute how much CO2 has to be in that magma, right? Magma fluxes are inherently difficult to estimate unless you are right there at the eruption. And Nyiramuagira eruption is an example that produced a magma flux. Albino et al. Made an estimate. So I just used that estimate, and it's about 0.3 cubic kilometers, erupted in about a year. So you have about 4,000 ppm of CO2 in that source of Nyiramuagira, right? So very high CO2 content in the magma that erupts. Now, what does that actually mean? How can we put this into perspective, right? And one thing we can do is we can look at people's work that have checked on, how do you actually melt the mantle, and that's a paper that recently came out. Oh, well, it's not recently anymore, 2017, and we see here that they use the depleted more mantle, and they have an average carbon content based on a lot of mid-ocean ridge basalt measurements that ends up being about 37 ppm CO2, right? So 37 ppm carbon, and that is about 137 ppm CO2. So if you have that amount of CO2 in the source, you can then produce melting at, about 250, 275 to 150 kilometers depth, right? So under mid-ocean ridges or in any situation, if you have that amount of CO2 in the source, you can melt the mantle at those depths. And the range of depth is very large. It's a 100-kilometer range, but it just depends on the temperature that you're looking at or the oxygen fugacity. And this paper goes into great detail about the conditions that are needed in order to melt in certain places, right? So here's, for example, 137 would be here. So it just depends on a lot of factors. But the point is that with that amount of CO2 in the mantle source, in the source rock, you can melt that rock at quite deep levels, okay? So now, if you take Nyiramuagira, which has this 4,000 ppm CO2 in the melt, if you assume a 10% melt fraction and you convert CO2 to carbon, you get about 100 ppm of carbon in the source, right? So that means that, for this, we have 37 ppm in the mantle source, which would be the MORP source. And for Nyiramuagira, we have 100 ppm carbon in the source. So theoretically, you can melt very, very deep. The rock that produces the magma that erupts at Nyiramuagira, Nyiragongo, is, according to these flux calculations, is very rich in CO2, 100 ppm, and so therefore it can melt at quite deep depths, right? Lower than 250 kilometers. Now, let's look at diffuse degassing in the East African Rift. And we've done some work with Bernard Marti and Raphael Pick in the northern part of the rift, in the Ethiopian Rift. And this data is not published, but there's very few CO2 emissions unless you're right on the fault, right? So these are some of these big faults along the rift axis in that segment. And as soon as you're on the fault, you get really high CO2 emissions. Now, the same is what we observed in the Magadi Basin down here in the Kenya section of the rift, and we see again, as soon as we're on the faults, we get very high CO2 flux. Now, Hunt et al. Has shown the same thing further south in the main Ethiopian rift, where they see high CO2 emissions close to volcanoes and close to faults, whereas away from those, they get relatively low emissions or no emissions at all. And our work with Lee et al., we looked at this in the Magadi Natron area in detail, and again, you have these border faults, the Natron fault in the Natron section. This is the cross-section B to B prime. A to A prime is over here. In the Magadi section, this is an Nguruman border fault. And again, along these faults, you have earthquakes. And along these faults, you also have the CO2 emissions, which is shown here. Sorry, this is kind of low resolution. But here's is a fault, and then the highest fluxes are really recorded along close to those faults. And carbon isotopes help us to identify the source of this CO2. And what we see is that, yes, these gases are, or the CO2 has a lot of air mixed in, right? They're very, very dilute samples. But if you extrapolate to the source with 100% CO2, you would get some sort of mantle contribution. If you have a divergence from that mixing line, that's probably due to biogenic CO2, right? So the point is that CO2 is focused along faults and that it has a mantle contribution to it. And that's what we published back in 2016 and 2017. Again, if you look along this Magadi-Natron area, and here's an example where along the faults, we have the highest fluxes, and in between those faults, we don't have very high fluxes at all. It's kind of background. And then magma bodies at depth might be producing some of that CO2, might be related to that CO2 degassing at the surface. So it's these kinds of studies, right, that I'm showing here that produce the CO2 flux numbers that you see in papers. And it means people have to go around and make those measurements on the ground, walk around with these flux meters and make the measurements. And then you extrapolate from your region. You may make measurements of 1,000 points or 1,500 points, and then over an area of a few kilometers. And then, of course, you're going to extrapolate to the entire rift. And that's as always in geology is tricky, right? Now, how much can we supply the CO2 flux by magmatic extension? And this is a very nice work by Hunt and that group. And what they have done is simply take the minimum crustal magma flux into the rift that assumes is related to the extension that's accommodated is accommodated and is exclusively accommodated through the dike intrusion. So it's a magmatic extension type scenario. And so if you have the extension rate, you get the magma flux. And if you have then the emissions of CO2, you can then estimate how much CO2 is in the source, right? So that's shown here in this blue arrow. So here, initial CO2 concentration weight percent in mantle melt assumes 10% melt fraction of mantle rock. So 0.4, 0.8, and so on. And here's the extension rate. So this is the Eastern Rift from their study, which shows this flux of CO2, 5 or whatever to 35, and for the entire rift. So in order to get those fluxes and with those extension rates that are reasonable for these different sections of the rift, KRV, WR, and so on, MER, main Ethiopian rift, you can then produce the flux that you see, given that you assume these CO2 concentrations in the source, right? Now, if you go to these very high extension rates, fluxes, that based on Lee et al., for example, it gets very difficult to reach that. Okay. So now the average CO2 concentration in a morp type mantle, if we assume a morp type mantle and a 10% melt fraction, we would have 0.14 weight percent CO2, which would plot around, which would be around here, right? This is 0.4, and 0.14 would be down here. So it's actually, in fact, it's too low of a concentration to explain any of the fluxes that we measure in the East African rift, right? Even the lowest fluxes of Hunt et al., you would have to have higher CO2 concentrations in the source than what you would expect in a mid-ocean ridge type mantle. And that's, I think, an important message. There's additional CO2 that is needed And so there's a quest for where's that CO2 and where's it coming from? Now, recent study by, this is actually recent study by Rice and others, they had some very nice seismic data, long-term deployment in the Oldonyo-Lengai, Ketumbei, Negelai region. And what they postulate based on their data is that they have this deep seismicity and that there are degassing paths of fluid release from depths that make their way up to the surface. So again, there's the seismic evidence for some deep CO2 movement that again is exhaling from some sort of magma body or some rock somehow makes it up to the surface and produces the seismicity. Now let's talk a little bit about this requirement of getting the CO2 to match the extension rates, or how can we get to the amount of CO2 that comes out, and how do we tie that to the magma flux, which is again tied to the extension rate. Here's a diagram from Muirhead that he put together. This is the mean magma flux in cubic kilometers per million years is shown here. And then this would be the weight percent CO2 in the source. And you see, in order to produce the flux, if you have high CO2, this is for 1 megaton of CO2 per year. Remember, we're about at maybe 4 megatons in Natron Magadi. But this is the order of magnitude we're looking at. Right, so if you have 10 weight percent CO2, 1 megaton, you can get the magma flux of 25 cubic kilometers per year. So again, if you have lower CO2 contents in your source, in order to produce that flux, you gotta have a higher magma flux, right? So that's the relationship. And again, if we have 0.14 weight percent of CO2 in that source that was proposed by Hunt and others, you have a very low amount of CO2, and you can't really explain the fluxes, right? No matter how much magma flux you have, it's very difficult to explain those high fluxes. Okay. Now let's look a little bit. Okay, let's look a little bit at the relationship between the CO2 that comes out in the rift part of East Africa and the craton. And there's a really fascinating, I think, very fascinating relationship here. And of course, this is very obvious if we think about it, but still, it was surprising to us when we did this. And what we're looking at here is that this is the East African Rift, and this is, of course, Oldonyo Lengai over here, and we see the Natron Basin and the Magadi Basin, and then we go further south into the Manyara Basin, and then we get onto the craton, which is represented here by the Balangida Basin. Essentially, we're going from the rift, which is represented by Magadi Natron, into the craton, which is kind of a transition, Manyara, and then really into the craton Balangida Basin. And what we found when we made our measurements a few years ago was that the flux of CO2 drops dramatically, right? Now, these numbers are pretty high, 76 grams per meter square per day. Over here, 30 in Natron, still pretty high. Then you go to 17, and then it drops down to 6, which is just barely above background. So you have a drop of CO2 as you go from the rift to the craton, which means that not a lot of CO2 is coming out of the craton. And the carbon isotopes are scattered, but still we can see that Magadi Natron has values that extrapolate to mantle, whereas Manyara, Balangida are very light values. So they're quite contaminated by some kind of organic source. And the helium isotopes show that very, very strikingly as well. For those of you not familiar with helium, helium 3-4 ratios are a really good tracer of mantle-derived fluids that carry that helium. So you can analyze the helium and you can get a sense of the fluids that carry that helium. And mid-ocean rich basalts or morph type fluids would have a helium 3-4 ratio of around 8, which would plot over here. And subcontinental lithospheric mantle SCLM would have a 3-4 ratio of about 6.8. And as you go down in 3-4 ratio, which is expressed as the ratio relative to air, you get to more and more crustal contribution, where 100% crust contribution would have a ratio that's less than 0.1 of the atmospheric ratio. And what we can see here is that Manyara and Manyara, I have to move this thing so I can see it. So Manyara Basin and Balangida, and those have very low helium 3-4 ratios, whereas the main Ethiopian Rift and Natra Magadi Basin have these much higher ratios. Okay. That means that in the Rift, we have more of a mantle helium influence, whereas on the craton, we have a crustal influence. Exactly what you would expect with that. Okay. Now, this is just showing the same thing. Now with a cross section, where I'm plotting the helium isotopes, and here you go from Manyara Balangida Basin, which is here, very low 3-4 ratios, up to Oldonyolengai here, and then you go back down into the Rift, where you have high ratios, and then they drop down a little bit. Right? Now, the CO2 flux mimics that. You have low CO2 flux on the craton in Manyara Balangida, and you have high CO2 flux once you get to the edge of the craton and then into the Rift. And this is a seismic image that shows the craton boundary. And what we see is that the craton boundary, that's right here, that's the craton boundary. And as you go into the Rift, you have this low velocity and significantly lower density. And therefore, that could indicate that we have some higher temperatures or fluids. Something is certainly changing as you go from the craton to the Rift. And the CO2 emissions and the helium isotopes clearly show that relationship as well. This is the same thing again, giving you some, this is the reference I was looking for. This is Tiberi et al. Sorry, I didn't have that on the previous slide. Very, very important study, Tiberi et al. That shows us where's the craton boundary and the changes in velocity and density as you go from the craton to the Rift. So it's a very, very big change at depth in terms of the seismic imaging, the tomography. Now, I hinted at that, but just want to emphasize that Oldonyolengai, the world's only active carbonatite volcano, sits right at the craton boundary. And it's exactly where you have the highest 3-4 ratio, 6.8, very consistent. We've measured it many times over the years, and it doesn't change. So 6.8 Ra is the highest in that region of the rift, as far as I know. And it's like right on that craton boundary. As you go away from Oldonyo-Lengai into the rift, the ratios drop down, 4, 3s, and so on. And likewise, the flux of CO2 is highest at Oldonyo-Lengai. And as you go, further over, there are these high values that are related to the faults. But a lot of those low ones are just related to what we measure everywhere where there's not a fault necessarily. But still, you see a big contrast in CO2 emissions from the craton. Now, based on the seismicity, what does this mean? Does this mean we have melting depths at 50 to 200 kilometers? Perhaps that's what it means. Maybe seismologists can tell us more about it. But it could be that there is some melting happening, or perhaps there's some CO2 release that occurs at those really, really deep depths. Here's Oldonyo-Lengai. Okay. And you can see this is the Rift Valley looking at Oldonyo-Lengai. There's these big cracks here, and there's some guys walking around. I guess this is our team looking at those faults, and we measured inside of those faults, and we measured everywhere over here. But the biggest flux is really at Oldonyo-Lengai. Not surprising if you look at all these carbonatite magmas that come out of the volcano as well. So I don't know if that paper, MESCO in class, has been published. I wanted to check that before giving this talk, but didn't get around to it. At any rate, there's a very, very nice study that Connie Klaas shared with me a few years ago. And what they found was that this is based on rocks and phenocryst assemblages and petrology, essentially. And what they come up with for the Rungwe region, and that's to the south of what we've been talking about, that's where the two rifts come together around the craton. Rungwe is a volcanic complex in that area. And their samples suggest that you have melting at pretty deep depths of 60 to 80 kilometers. And importantly, it is important to note from their study that you have to have CO2 and water for getting melting. So here are the solidus for CO2 and water. This is the hydrated solidus, and we see that we need hydrated solidus or CO2 and water for rocks to melt in that region, and again at relatively deep depths. Again, these are papers in prep. I have to check if those are out yet. Probably they are. So here's the Rungwe region. Again, this is a region with large emissions of CO2. This is a travertine mound in that region. We haven't done the CO2 fluxes from that area, but I would assume that there's high CO2 flux. We measured the springs, and based on the spring fluxes, Peter Barry had a paper probably 10 years ago now, where he estimated the CO2 emissions from those springs, getting a sense of how much CO2 comes out of that region. Again, it's probably pretty high. Now, if we plot that on the diagram, this is the Rungwe depths. This is Nadro Magadi Basin based on that melting of Tiberi. You see that these melting depths are what we can expect, right, for that area. And however, with those melting depths and with those amounts of CO2, yes, you can melt the mantle, obviously, with 30 ppm, 37 ppm CO2, and you can produce melts with that amount of CO2. However, you can't really get to the CO2 fluxes that we have measured in those areas, right? that we have measured only in two areas, really, in the Natural Magadi and Balangida and so on, as well as in the main Ethiopian rift, right? Even though you can melt the mantle at those depths with the amount of CO2 that would be in a moored mantle, you would still have to have additional CO2 to explain the CO2 fluxes that are measured at the surface. Now, again, for near Muragira, if we have 100 ppm CO2, and at Oldonyulengai, an absolute maximum of 300 ppm carbon in the source, this is based on work we did back in 2009, you could melt much, much deeper, right? If you believe that you have such high CO2 contents in the source, which I explained to you is based on, for example, the near Muragira CO2 emissions and the magma flux at Oldonyulengai is a similar kind of calculation. And so you can play those games and you could say, well, there is higher CO2 content in the source. So you could potentially melt significantly deeper. Timing wise, I think I'm gonna skip around this. This is just, it's written up in our paper, but it just shows that carbonatites are all concentrated around the craton. And it's just, again, an argument that CO2 seems to come up and around the craton and produce things like carbonatitic magmas. This, again, is from Curry and Van Beek's very nice modeling paper that's also included, or that we looked at with Murrayhead's paper, the Nature paper, where essentially it shows that you can just produce a rift if you just let it sit, and if you have the density contrast of the cratonic mantle and has a density contrast compared to the underlying mantle, and over time the rift will just start to form, and you don't need to have any extension or anything at all. And carbonatites could form right here at the boundary if that density contrast is in fact due to additional carbon that accumulates in the cratonic mantle lithosphere. And that's essentially coming back to this model where we have the Natural Magadi area here, and you have the craton. The craton has been metasomatized over time, and then that material moves over into the rift axis and produces melting, lowers the solidus, and then you have melting, and those melts ascend into the rift area, and that also produces the high CO2 flux as those melts degas. Whereas in the Balangida-Manyara region on the craton, that process is not happening. There's no migration of melts up towards the surface. There's no migration of cratonic lithosphere that moves that carbon-rich metasomatized material over to the rift where it actually produces melting. And again, this is a paper that Steve Foley and I put together. It's kind of a conceptual idea of where do you get all this carbon coming from? Where is it coming from? It could come from accreted arcs. It could come from plumes. And Steve Foley did a calculation to show in that paper that you can accumulate quite high amounts of carbon at the base of the craton over time. And if that carbon gets mobilized, it can move into the sides of the craton and potentially produce these carbonate-rich melts and carbonate volcanism, carbonatitic volcanism. We can look at that. We can think about how do we accumulate carbon under the craton, and this is very easily done. with a mass balance. Essentially, you have an outflux of CO2 from arc volcanoes, and you have a carbon input into the subduction zone. And these two things aren't balanced, right? And that's been known for a long time. There is more carbon input into the subduction zone than what comes out at arc volcanoes. And it seems that that observation seems to hold, has been holding for decades now. And then what you can say, and that's what Kellerman and Manning have done, is where does that carbon go, right? There's essentially a number of ways it could go. Maybe your measurements are wrong, right? But if you believe your data, then either that carbon goes down into the convecting mantle, or it gets stored, right? And that's the solid storage idea that they put forward. And the big errors on these numbers, because we don't know how to distinguish between what goes down into the mantle and what gets stored, right? You don't, in either case, you don't see it. And however, if you accept the solid storage idea, you can then take those solidly stored carbon blobs or whatever they are and accrete them to make cratons over billions of years, and then you can come up with additional CO2 that's stored under the craton, which then gets remobilized by these processes of rifting. And that is one way, perhaps, of explaining the high CO2 emissions that we see not only at not only extrapolated in the over the entire rift, but also in places like Nyiragongo, Nyamuragira, Oldonyulengai. Although I have to say that we still don't know very well the CO2 flux from Oldonyulengai, at least not currently. So that is, again, the overarching model, right? You have this carbon that is accumulated underneath the craton, and suggesting that it is brought in from accretion of arcs, that it is brought in by plumes, and that that carbon gets mobilized, moves to the side, and produces melting of the mantle. Those melts, they ascend, and as they degas, they produce a high CO2 flux. And at the edges of the craton, this process somehow is very enhanced and produces carbonatites. Okay, so this is just some details about the model. Anyway, you can read the paper of Curry and Van Wyck, 2016. Essentially, they explain that if you have a cratonic lithosphere of a certain thickness that has a density contrast, it will simply stretch and will produce a rift. And how do we get this density contrast? Now, that's where we propose you have this carbon that accumulates and helps that density contrast. All right, I'm going to skip that. Okay, so these are some broad conclusions. We think that the carbon content in the source of the East African rift magmas is bigger than the depleted Moab mantle. And that's based on the emissions, right? That's really just based on that. And we think that you need CO2 for melting. Now, you could melt at those depths with Moab type mantle CO2 amounts, but based on fluxes from Nyiragongo, for example, or Oldonyulengai, where we don't know the flux very well, but we think it's pretty high, you probably need to have additional carbon. And we propose that you have carbon enrichment under the craton to drive these things, to drive the formation of the rift and the formation of carbonatites. However, I want to emphasize that volatile fluxes from the East African rift remain very poorly constrained. We have talked for an hour almost about CO2 and a little bit about helium. We haven't talked at all about other volatiles like water, like sulfur, chlorine, helium fluxes, for example. And again, that work hasn't been done very much, and those fluxes remain poorly constrained. So I think what we need in the future, and this is just a list, maybe we could combine extension models that account more for fluids, have more melt inclusion data, and there's exciting new data coming out by Mary Jo Browns in a paper that's submitted now with new melt inclusion data from rift magmas. Perhaps we need MT to detect fluids better, and there has been some recent work on that to constrain the magmas, locations in the crust, get PT from petrology, and better interdisciplinary synthesis. As usual, I think if we work across disciplines and join our forces, we can address some of those remaining mysteries about the East African rift. So that's all I have. Thank you.
Thank you very much, Tobias. It was a superb talk. Thank you very much. The floor is open for questions. So either you unmute yourself and you ask Tobias a question, or you put it in the chat. So Sasha, yeah?
Thanks for this nice talk, Tobias. You showed one line where you did CO2 measurements in a FAR, Manda-Hararo segment. I'm curious about how much space did you cover in a FAR? How far did you go around? Did you find some active faults that degassed and some that did not? Do you have enough data to do some kind of upscaling?
We have very little data, and we just focused. I was there only one field season, and Raphael and James went back one more time, I believe, and I shared the plot, and it's just very few data points. But what I see is that they went 4 kilometers, 8 kilometers, 12 kilometers. 15 kilometers away from the rift axis and found nothing. The only, as I showed already, the fluxes were high right on those faults. Therefore, in order to extrapolate and to get at a CO2 flux from that region, you'd have to know pretty well where the faults are, and then you would just have to assume a certain flux and then try to make that extrapolation. We haven't done that yet.
Okay, thanks.
Yep.
We have a question by Robert. Robert, you can ask a question.
It's my morning. Good morning. Good afternoon. Thank you for this nice talk. I'm a metamorphic person. I've read almost none of the papers that you've cited, but I do have a question. You speak of carbon mobilizing. And it's my intuition that says that the form of carbon in the lower crust and in the mantle is probably graphite, or if deep enough, diamond. And then you speak of carbon being mobilized. And my intuition says that the carbon in graphite is really quite inert. And so the only way to mobilize it is to oxidize it. But oxidation, oxygen fugacities down there may not be very high. And so I'm wondering how maybe part of the problem is the oxygen balance, because carbon is around. So now maybe the CO2 flux is also a direct function of oxygen fugacity. If we say carbon is lots of places, but oxygen is not. And then I'm wondering, well, the little bit of intuition I have from rift basins is if they are fluvial sediments, they will be highly oxidized and could even have a hematite cement. So now if we bury those sediments with all that oxygen bound in ferric iron and mix it with graphite, now we can make the CO2. So I wonder, are any of the ideas that I have germane to what you're talking about?
Yeah, I think these are really important points. With Steve Foley, we looked at that a little bit in the paper, and one of the suggestions or one of the proposed ideas, the paper is actually a perspectives paper, and it is supposed to trigger some conversation. And some of the ideas we put forth is that plumes help with mobilizing that carbon, and perhaps also bringing some more oxidized materials into that region to move the carbon. But you're absolutely right. The carbon has to be perhaps has to be oxidized. We actually think that it can just move as a solid phase. It doesn't need to move as a CO2. It is a solid phase. You know, part of the solid rock, and it moves because of the density contrast. That's the model of Jolante that she has published in that modeling paper. As long as you have density contrast of solid material, it'll move.
So you're saying the carbon, let's call it graphite, the graphite can move independently of the rocks, of the minerals around it?
I think it could I don't know, but couldn't it possibly move as part of the rock that it's in? Thinking of having, you know, pieces break off and move to different places from the craton towards the rift as the rift is forming. It's essentially like abrasion. It's like taking material down a subduction zone, like eroding the crust and shoving material down into the subduction zone, crustal erosion, for example, something like that. Now, of course, you know, I'm not an expert in this, and somebody has to model this probably properly to see if this is even feasible.
I think I understand. Thank you.
Okay. I have quite a long comment in the chat, so I'll try to read it with my French accent. Congrats, Tobias, a highly educative presentation. I'm working on the 3-ton layered igneous complex of Sierra Leone, West Africa. It's called FLIC. The FLIC has been shown by me and others to be a heat source that initiated the rifting on Pangea some 200 to 205 million years ago. Because I couldn't get the right minerals, paragenesis to constrain the PT conditions of emplacement of the FLIC, I opted to do microthermobarometric studies on the cumulus, plagioclase, olivine, pyroxene, and apatite phases to see if I could get well-defined isocores from which I could deduce the PT estimates. To my great surprise, all the mineral phases show abundance of CO2, H2O, H2O, and CH4. Everything being equal, I believe that these fluids are not originally from the mantle, but from the sediments and other sources that were incorporated into the mantle during the accretional processes that led to the formation of Pangea in the first place. Don't you think that your CO2 sources can also be similar to those of the FLIC?
So I think he is saying that those fluids come from sediments,
Yes.
and that they are not from the mantle. Now, yeah, that's always the question, right? does the CO2 come from the mantle? And we can address those with carbon isotopes, for one, and with the helium isotopes. Now, the carbon isotopes in places like Oldonyolengai and in some of the springs are very clearly mantle. They're -5, -4. The helium isotopes are high. So, some of it has to come from the mantle, but you can always have mixing. You can have a contribution from sedimentary sources, right? From limestone breakdown, from organic sediments, and to really tease it out, you'd have to have a lot of samples to really see, is it mantle or is it sedimentary? When we go from the rift to the craton, we see this big change in carbon isotopes. The carbon isotopes become very, very light once you get onto the craton. And that tells me that, well, yeah, on the craton, there's very little CO2. And what there is biogenic, shallow, sedimentary stuff. Whereas when you go over to the rift, it's different. And it's much more mantle derived.
Does it respond to your question, Ibrahim Barry?
I think you're muted.
Yeah, I think he's muted. Let me ask to unmute so he can respond.
Was I muted in the beginning?
No, it's because someone came in and there was some noise which I was trying to.
Oh, okay.
Which I thought would, and then the click went onto yours instead of that person. Sorry.
Oh, okay.
Okay, so I'm not sure either. Any other question? Okay, it doesn't look like. Myself, I just have a question, Tobias. Like the helium ratio should be a very good indicator if it comes from the mantle or not, right?
Yeah, that's the accepted paradigm. Yeah.
Okay.
Yeah, absolutely.
Yeah.
So, but people will say, okay, the helium comes from the mantle. Does the CO2 come from the mantle? But the thing is, the helium doesn't go by itself. The helium is transported by CO2 because CO2 makes up a huge amount of the fluid, and it transports the helium. And so if the CO2 transports the helium and the helium has a mantle composition, then we always assume that CO2 also has a mantle source.
Yeah. Okay. Okay, thank you very much. I think we don't have any more questions. I would like to thank Tobias first for his very good presentation. Thank you very much, Tobias. And also everyone for joining to listen to us. Thank you very much. So I'll stop the recording.
All right.